Dear students, I am Dr. Srilalitha, in charge physics, assistant professor at MVSR Engineering College, Nadargul. This is a lecture about magnetic materials, which is divided into two parts. So this is the first part of the lecture, where in this lecture, the topics which I am going to cover are basically, before starting the lecture, I want to discuss about the introduction about this topic, that is about the magnetic materials. And let us continue after going with the introduction. Let us continue with some terms and definitions, so which we all are aware of some of the definitions and origin of the magnetization, and end up this lecture with the classification of magnetic materials. So before going to this topic, what is a magnetic material? What is a magnetic material? Any material when kept under a magnetic field, if at all it gets magnetized, then we call it as a magnetic material. For example, if you take a small iron pin, take this iron pin and get it nearer to the magnet, what happens? It gets attracted. So it is a magnetic material. If you take a chalk piece and keep it under a magnetic field, will it attract? No. So it is not a magnetic material. So when kept under an external magnetic field, if at all it is getting attracted, then those materials are called as magnetic materials. So here you can see a small pick where a small magnetic rod is taken and brought nearer to the iron pins. So they are getting attracted. So all these iron pins belong to magnetic materials. Right? So here in this lecture we are going to discuss in detail about some different types of magnetic materials. So why should we read all these why this magnetic materials are introduced in our syllabus? Why? Because magnetic materials play a prominent role in modern technology. They are widely used in industrial electronics, entertainment electronics, and computer industry. The methods of information storage are based on magnetic storage techniques. These materials play an important role in information storage devices. So that is the reason why we are studying about these magnetic materials. Here in this presentation here, I have given some examples like what are those: power generators, transformers, electric motors, radio, television, telephones, computers, and some of the components of sound and video reproduction systems. So all these are applications of magnetic materials. So what are some of the terms? Let us discuss about a magnetic dipole. What is a magnetic dipole? Magnetic dipole moment, magnetic induction or magnetic flux density, and magnetic field intensity H. Magnetic dipole. What is a magnetic dipole? What are the magnetic dipoles in a magnet? North pole and south pole. So there are two equal and opposite magnetic poles which are separated by a small distance. So that magnetic dipole moment is introduced by mu, which is equal to the product of pole strength and length of the magnet. Right? And then the third one is magnetic induction, which is represented by B. So before going to this magnetic induction, what is flux? Flux density means magnetic line. So when a material is kept under a magnetic field, so depending upon the strength of the applied magnetic field, that is the external field H, which we generally represent it with H. So the magnetic lines of force will start penetrating into the material. As the strength of the applied field is going on increasing, the number of magnetic lines will be going on increasing within that material. So that is the number of magnetic lines of force is called as flux. And the magnetic lines of force per unit area is known as flux density, and which is nothing but magnetic induction. So magnetic induction is directly proportional to H. That is, B is directly proportional to H. So H is equal to, we can write it as B, or magnetic induction B equal to mu H, where mu is called as proportionality constant or magnetic permeability. So magnetic permeability can be expressed as mu is equal to B by H. So it is a ratio of the magnetic induction to the applied magnetic field intensity. Magnetic susceptibility, it is the ratio between the intensity of magnetization to the applied magnetic field intensity, that is Xi. Magnetic susceptibility is represented with Xi. So Xi is equal to I by H. What is I? Intensity of magnetization. What is intensity of magnetization? It is the process of converting a non-magnetic material into a magnetic material. So that generally represents when a material is kept under a magnetic field. So these are the terms which should be where we should be aware before going into the topic. So what is magnetic? What are magnetic dipoles? Magnetic dipole moment, magnetic induction, intensity of magnetization, magnetic permeability, magnetic susceptibility, and external magnetic field, that is H. Origin of magnetization. So the origin of magnetization is basically due to the three main reasons. That is, one is the orbital motion of electrons, spinning motion of the electrons, and the nuclear spin. So this is a figure. From this figure, you can observe that this is the nucleus, and around this nucleus we have an electron revolving in different orbits. So one orbit can be considered as one orbital magnetic moment. And where the electron will spin and revolve around the nucleus, so that is called as spin magnetic moment. So this orbital magnetic moment and spin magnetic moment are the main reasons of magnetic dipoles, which can be considered as magnetic moment. That is, the magnetic properties of the solids arise due to the electrons which are undergoing different motion in the atoms, that is, which give rise to magnetic dipole moments. So these magnetic dipole moments are responsible for the magnetic properties of materials. In general, the magnetic dipole moment of an atom arises due to three main reasons, that is, orbital motion of electrons, electron spin, and nuclear spin. What is orbital motion of electrons? The atom of any material consists of a certain nucleus and electrons which moves around the nucleus in specific orbits. I have given the explanation here. Each electron orbit is equivalent to a tiny current loop, and it behaves as an elementary magnet having a magnetic dipole moment. The total orbital magnetic moment of an atom is the sum of orbital magnetic moments of all the individual electrons. Right? So when it is when the electron is in an orbital motion, it also will have a spin motion. So each electron spin is also about an axis. So that also can be considered as magnetic dipole moment. Even there is a nuclear spin in addition to the nuclear spin, in addition to the orbital motion of the electrons and electron spinning motion of the electrons. But this nuclear spin is 1 by 2000 times of the electromagnetic moment of an electron, and hence it is neglected. So this is the origin of the magnetization. So when an electron revolves around the nucleus, so whatever that current loop it is having, it is considered as one magnetic dipole moment. So classification of magnetic materials. Basically, magnetic materials are classified based on permanent magnetic dipoles. So it is based on that. It is classified into two parts. The first one is the one where there are magnetic materials which are not having permanent magnetic moments. The example is diamagnetic materials, and the other is the one which are having permanent magnetic moments. So we are having four different types here depending upon the direction of the spin. So they are paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and fourth one is ferrimagnetic materials. So in this class we are going to discuss about these 5 different types of magnetic materials. The first one is diamagnetic materials. So generally when we are discussing about diamagnetic materials, the first point is that the materials which do not have permanent magnetic dipoles are called as diamagnetic materials. So these do not have permanent magnetic dipoles. So the second one is that Here you can, from this figure, you can see that this is a diamagnetic material. So when a diamagnetic material is taken and kept under a magnetic field, you can see that the magnetic lines are away from the specimen. So that is, they are opposite to the direction of the applied field. So what are diamagnetic materials? Materials when kept under a magnetic field, if they get feeble magnetized opposite to the direction of the applied field, then we call them as diamagnetic materials. They acquire very feeble magnetization. Feeble magnetization means very less, and hence they exhibit negative magnetic susceptibility. So here it is of the order of 10 power minus 6. The magnetic susceptibility is very less, and it is of the order of 10 power minus 6, and relative permeability is very much less, and it is less than 1. These diamagnetic materials are independent of temperature, right? And some of the examples of diamagnetic materials are inert gases, organic compounds, hydrogen, air, water, gold, silver, and bismuth. So these are some of the examples of diamagnetic materials. So once again, what are diamagnetic materials? First point, they do not possess permanent magnetic dipoles. Second point, they get feeble magnetized when kept under a magnetic field, but it is opposite to the direction of applied magnetic field. Magnetic susceptibility is very less, and it is negative. Relative permeability is less than 1. And magnetic susceptibility is of the order of 10 to the power of minus 6. They are independent of temperature. So these are some of the points of diamagnetic materials. So this is the basic classification between paramagnetic materials and diamagnetic materials. Diamagnetic materials are repelled by a strong magnet, whereas paramagnetic materials are attracted by a strong magnet. So what are paramagnetic materials? The first point, that is, when a magnetic material is kept, that is paramagnetic material, when it is kept under a magnetic field, it gets feeble magnetized, but it is along the direction of the applied magnetic field. And all the spins, all these materials, that is para, ferro, antiferro, ferri, all these materials possess permanent magnetic dipoles. But here, especially in the case of paramagnetic materials, all the spins are random in direction. All the spins are randomly oriented, and hence the net magnetization becomes 0. But as they are along the direction, even though they are feeble magnetized, that is very less magnetized, they are along the direction of the applied magnetic field, and hence their magnetic susceptibility, of course, it is very less, but it is positive. And it is also of the order of 10 to the power of minus 6, and the relative permeability is greater than 1. So field lines are pulled towards the material and permit through it when it is placed in a magnetic field. They are strongly dependent on temperature, whereas diamagnetic materials, they are completely independent on temperature. Some of the examples are oxygen solution of iron salts, copper chloride, chromium. These are some of the examples. See, from this figure you can observe that in the absence of the field, all the spins are aligned in different directions. All are aligned in different, but when field is applied, they are along a particular direction, and it is along the direction of the applied field. And from this figure you can see that some magnetic lines are coming closer to each other, right? So this is about paramagnetism. The next one is ferromagnetic materials. Ferromagnetic, this is a special class of materials, magnetic materials. They are these materials possess strong magnetization, very strong magnetic field. When they are kept under a magnetic field, they get strongly magnetized. What is the reason? Why? Because what is the reason why they are strongly magnetized? Why? Because it possesses spontaneous magnetization. What is spontaneous magnetization? The materials which possess magnetization even in the absence of applied magnetic field is known as spontaneous magnetization. And the reason that is, there is some internal magnetization within a ferromagnetic material. The reason behind it is it possesses magnetic domains. What is a magnetic domain? Here you can see the figure. This is a figure of a magnetic domain where the ferromagnetic material is divided into different regions, where in one region the spins, but you can observe that in all the regions, that is even though the directions of different regions are different, you can see that In a particular region, all the spins are aligned along a particular direction. So this is a magnetic domain. What is a magnetic domain? It is a region where all the spins are aligned along a particular direction. It is called as magnetic domain. So due to the presence of this magnetic domain in a ferromagnetic material, it possesses some internal field. The presence of this internal field is known as spontaneous magnetization. And due to the spontaneous magnetization, these ferromagnetic materials possess, they are strongly magnetized when kept under a external magnetic field. They are highly dependent on temperature. And from this figure, you can see that all are aligned along the same direction. All are aligned along the same direction. But the other important point in ferromagnetic materials is that they exhibit hysteresis, and relative permeability is very large. What is hysteresis? Hysteresis is a lag behind the magnetization. Lagging means, so generally when you plot a graph B versus H, B is directly proportional to H. So when you plot a graph B versus H, it should be a straight line. But for ferromagnetic materials, it is not a straight line. We are getting a hysteresis curve. The reason once again behind it is due to the presence of magnetic domains. What is a magnetic domain? It is a small region where all the spins are aligned along a particular direction. So, and these ferromagnetic materials are highly dependent on temperature. So at a particular temperature, the magnetic susceptibility is constant, but when you further increase it, when the temperature of the ferromagnetic materials is increased at a particular temperature called as Curie temperature, all the spins will become random in direction and ferromagnetic material is converted into paramagnetic material. So from this figure you can see this is a figure which is drawn temperature versus susceptibility. So this is the case with the paramagnetic material, but for ferromagnetic material up to Curie temperature you can observe that the magnetic susceptibility is constant. But when you are still increasing beyond Curie temperature, there is a sudden fall in susceptibility, and it shows that at this temperature all the spins will be random in direction, and hence the net magnetization will be once again 0, and the ferromagnetic material is converted into paramagnetic material at higher temperatures. Right. So this is a figure of where it shows the spin where all are aligned along. So it is composed of domains where all are aligned along the same direction, but all the domains are in different directions. So the net magnetization here also it becomes 0 for a ferromagnetic material. The next one is antiferromagnetic material. The basic difference between ferromagnetic and antiferromagnetic material is that in ferromagnetic material all the spins are aligned along the same direction. In antiferromagnetic material it is observed that the neighboring spins are opposite in direction and equal in magnitude. You can see the figure here. Previously for ferromagnetic materials it is observed that all the spins are aligned along the same direction, but here the neighboring spins are observed to be opposite in temperature, opposite in direction. Right? Even this is also composed of magnetic domains, but still in each and every domain the neighboring spins are opposite in direction and equal in magnitude, and hence the net magnetization becomes 0. Even these materials dependent on temperature, but here we call it as a Néel temperature. So above Néel temperature the antiferromagnetic materials are converted into paramagnetic materials. The next one is ferrimagnetic materials. Ferrimagnetic materials are very much similar to ferromagnetic materials. Only the difference is in ferro and ferri, the neighboring spins, the magnitude of the neighboring spins is not same. Even though they are opposite in direction, it is observed to be that the neighboring spins are not of equal in length, and hence it possesses some net magnetization. Even they are highly dependent on temperature. Above Curie temperature, these ferrimagnetic materials are converted into paramagnetic materials. So here is the figure. Even these materials exhibit hysteresis character. Even they possess small domains, but you can observe that the neighboring spins are not of equal in magnitude. Right. So They are of course in opposite in direction, but as they are not of equal magnitude, they possess some net magnetization. They are anti-parallel. So this is about the basic differences between ferro, antiferro and ferri. You can see from this chart. So ferromagnetic materials below Tc, that is the critical temperature, all are aligned along the same direction, right? Antiferromagnetic materials below Tn. Tn means Néel temperature. Neighboring spins are opposite in direction and equal in magnitude. In ferrimagnetic materials, neighboring spins are opposite in direction but not in equal in magnitude. Paramagnetic materials spins are randomly oriented, that is, it is irrespective of Tc or Tn. Even though they are dependent on temperature, all are oriented in different directions. But once magnetic field is applied to a paramagnetic material, they try to align along the field direction. So this is the basic difference between dia, para and ferro. So this is the first column is the one where in the absence of the applied field, ferro and ferri, they are little bit, of course all of them are oriented along the same direction. In para they are oriented in randomly, and dia they don't possess permanent magnetic dipoles, right? So when field is applied, what is happening? They are opposing the field, but in paramagnetic material all are aligned along the same direction. And of course even in ferromagnetic and ferrimagnetic materials are also all are aligned along the same direction. So these are some of the some information about the classification of materials, about their spin, based on their spin and permanent magnetic moments. So if you, regarding this lecture, if you have any doubts, you can contact me or your subject teacher during your assigned hour.